I don't know. I personally find it very uninspiring. So I'd like to talk about some techniques for implementing proof assistance a little bit with a view of what's going on behind the scenes and what happens to our computational monad when we try to have more in our add more techniques to our proof checker. And the ones that I'm going to discuss are holes and unification. So maybe I can explain these things first. Slides. There we go. Okay. So what is a hole? So in general, when I think of a hole, I think of some sort of an unfinished or missing piece of formalization or code. You're writing code, and there's a piece that you as the user, you don't want to provide for some reason. Maybe it's an implicit argument. Maybe it's actually a hole you want to make there, but it's information that you haven't provided yet, or that should be provided somehow, but it is not there. And such holes, guys, so such holes, the idea is that the missing pieces of information will be provided at some point by some mechanism. But they will eventually be filled in. That's the idea. We're going to talk about possible examples. One important point is that when you have a hole, it's not supposed to block your proof checker. The proof checker is supposed to keep going, and sometime later it's going to find out what is supposed to be in that hole, and then somehow use that to its advantage and also recall what it is supposed to be. But the idea is that you can do other things even though you don't know what the missing piece of information is. So what are some examples? There are lots of examples, but maybe the two that are most familiar probably to most people here, especially if you've used ACTA before, or any proof assistant really, is interactive holes that you create, that the user will create, and then also the user will fill them in. So this is how the development works in ACTA, right? Write down a question mark, poof, hole is created, and then you can do other things. The hole is not blocking your development. And you can come later and fill it in. And when you fill it in, all the things you did so far must still work. They don't break. Another one where the hole is invisible, but it's there, is an implicit argument. So how does an implicit argument work? You define your function and you mark your argument as implicit. What this tells the type checker is that when it sees your function applied, then it knows that you did not provide that argument. So what it will do is it will put a hole in. It will say, oh, there's a missing argument here. Let me put in a hole. And then it'll keep going because it doesn't know what the missing argument is. So now it's a hole. And some mechanism at some point, in this particular case, it's going to be unification, is going to figure out, oh, that should have been such and such, and then it's going to do it. So these are examples of holes. You can take a very general view of this, and you can observe that, well, we can have many holes at the same time. They may be interdependent. Some of them might depend on others, and that sounds tricky. It maybe matters in what order you attempt to fill them in. That's also, it might be important because some of them may be more informative than others. So you get into a kind of a mess. But it's an important thing to do. It's an important thing to have. So we do want them. So I already mentioned this, that holes can be created by the user or by the machine. Maybe there's let's look at this. If the user in Agda, if you type, what's the difference if you type a question mark or an underscore? Because both of them are going to be a hole. Well, the difference is that if it's a question mark, you're telling Agda, I will tell you how to fill the hole. But it's an underscore, you're telling Agda, you do it. And then the way Agda works is it's going to complain unless it can see that this underscore can be filled in uniquely. Because the idea is that if there's nothing to be filled, then that's an error. But if there are several possibilities, it's probably a good idea not to pick one of them at random and say, hey, are you aware of the fact that there are many possibilities here? So, okay. Yes?
You say insert all the place on list arguments. Type checking. Don't you do that elaboration or?
Well, I mean, this is kind of a. So the question is, who will? You're asking about this line?
Yes.
Because your question is, wouldn't it be better to say that it's the elaboration that inserts holes?
Okay. Some other phase, basically.
Yeah, some other phase. Okay, so how do you know that you need to insert? How does the machine know that it has to insert an implicit argument? Where is the information about this fact stored? Because that's going to determine what phase it's going to happen in, right? And I can imagine at least two scenarios. One is that when you have your types, when you define pi, you have two kinds of products. You have a product with an explicit argument and a product with an implicit argument. So literally you write pi with ordinary or with curly braces, okay? And so if that's where you're storing it, then you will say, oh, I have an F, oh, it's a pi with curly braces, oh, I need to insert an argument because it's curly braces, I need to put in a hole. That would mean that the information is stored in the types. So it's very likely that it's going to be your type checker that needs to check this. Why? Well, because in order to even find out that the type F is this implicit argument product, you may have to perform a lot of work. Maybe you need to normalize the type before you even find out that there should be an implicit argument, right? So it's not maybe immediately apparent. So another strategy that would be, to my mind, a little more naive, would be to somehow have some phase, syntactic phase, which says, oh, the symbol F is going to have an implicit argument. So whenever you're parsing F, just stick in a hole. But I think that's going to be less flexible, because that will only enable you to have an implicit argument on symbols, associated with symbols, or something like that. But it might be the case that you have a complicated expression, and you do a lot of thinking about it, and then you realize, oh, there is an implicit argument next to it, let me insert it. And that's something that type checker does. So this is a very long answer to a short question. But I wanted to point this out, because it's important to think about where is information stored. Yes. And as a principle, you should be wary of storing information in 25 different places. So it's probably better to be well organized, and the things that have to do with concrete syntax maybe do not belong into the typing information. But in general, I think that you want the typing information to provide also things which Ambrush cannot see because he lives up high in some upper level, right? So okay. Now, what are holes called in your type theory? Well, there's another name for the holes. It's meta variables. So maybe first we should spend a little bit of time talking about what the hell are meta variables. So the meta variables are the things. So let me give you an example. So suppose I write this. Well, I'll just do a real example. The type, the formation rule for products. Yes. So what is this X? Well, this is here. It's a bound variable, right? What is this? Well, here it's also a variable, but it's not bound. It's a variable that's in the context. So in a way, it's bound by the context, but people would normally say it's a free variable that, so you would call the things which are here free. But what is A? Well, A is not a variable in the sense that it's in the context and it has a type. It's just a thing. So what is this thing? Well, that's a meta variable. You are using it to indicate that in that place will stand some expression of your type theory. So that's a meta variable. Like meta variables appear in schemes. In fact, all our inference rules that we have seen have meta variables. Also, gamma is a meta variable here, because one such rule, this thing here, is really parameterized by gamma and A and B, and it's a family of closure rules, to be quite precise. It's not an inference rule. You could also write it down as an inference rule, and then you would actually have a meta variables. And you could write it you could write something like this. Say I have a meta variable of type, and then I have another meta variable B, and now you need some notation. So in Andromeda it's like this. If X and A, then this is type. Something like that. I forget. And then you could write a rule down. So the meta variables are sort of one level up, and they literally correspond to pieces of your proof terms, or they're chunks inside your whatever you're doing, and they're holes. That's what they are. So holes are meta variables. That's one way to think of them. So what we are going to do when when somebody wants to have a hole, we're going to create a fresh meta variable and stick it in there. Okay, that's the idea. So introduce a new meta variable and stick it in there. Yes.
Why do we have to know their type?
Okay, so this is a good question. You don't necessarily have to know its type, and there are implementations where you have untyped holes, and you can do that. But in our case, we're just going to have types.
Okay, it's specific to our system.
Specific just to what I want to do here.
Okay.
I decided I wanted to have type meta variables because I'm always a little scared of things that are untyped. So I said, oh, let's have type meta variables. But you can do a lot without having type. Without having a type, they're just holes, and then they run around, and at some point you say, oh, I know what it's supposed to be, and you fill it in. Okay.
Would it be then reasonable to, like, if we have an untyped meta variable whose type we don't know, add a new meta variable for the type?
Yeah, that's a trick I rediscovered a week ago. I was very proud of myself. If you have a meta variable but you don't know its type, you just create another hole which is its type. And that hole, you know the type, it's type, right? So you say if I want to have a meta variable, but I don't know what its type is, so you create another meta variable. And what is the type of this one? Well, this one is type. Okay. What if you have universes? Then you don't know which universe it is, so you create another meta variable, and then you say this is the level. Good luck. Okay, so yeah, you can play lots of cool tricks and create lots of meta variables, and then you start to be sorry, or you optimize your meta variables so that things work faster. Now here's one point. If we decide that we want to know the type of the meta variable, then when we create holes, they need to be in checking positions, right? So when you have your term, some pieces of it will be inferred and other pieces will be checked. We want the holes to be where things are checked, because that's where we know what the type is supposed to be. But if it's inferred, then we're going to have a hole and we'll try to say, well, what is the type? There's no information of what it's supposed to be. So either you use this trick, that's one possibility, or you just complain to the user and you say, hey, I don't know what this is supposed to be. So do you know what Agda does?
Nothing.
If you just go in Agda and you just put like an underscore in a random place, what will it do? We can try later. Tell us what.
I think it creates another variable.
So how would you test this in Agda? What would you do?
Underscore equals question mark.
Well, I think you could just say, you could just like what happens in Agda if you just write how equals question mark without any type annotation of cow. What would it do? Because now it's because you see if in Agda first you test this, you say does this work in Agda, and then you write here something like 0. Okay. If this works in Agda without any annotation on cow, then clearly it inferred that 0 is a nat. Okay. And now you go and you put in a question mark. Well, now it has a problem. This is a hole in an inferring position, so something might go wrong. Yeah? Another place where we know kind of for sure that this inferring position is if you have an application, the head of the application. So if you want to be really nasty, write this and ask Agda, what do you think this is? See what happens. I'm inviting you not to listen to the lecture and play with Agda, which is maybe not very smart. Okay. Now, what does it mean to fill a term, to fill a hole? Okay. So somehow somebody tells you, or you calculate that your meta variable should be equal to such and such thing. You want to fill the hole in with the term. Well, that would mean that now you need to substitute this term for the meta variable. But in the meanwhile, so there are a couple of things that are going to happen. So you will discover what this term is somewhere else, not where the hole is, right? Your computation checking will progress. You're over here, you're inside 17 lambdas, and you say, ooh, I know what this hole is. So it's quite important to keep in mind that the place where you find out how to fill it in and the place where you created the hole may be quite unrelated. In particular, they may happen in different contexts. And that is going to be a problem because you're not supposed to blindly take something from one context and just stick it into the other context. So we have to be careful. Okay, what do we do there? So that's just a caveat. So what would be a reasonable solution? Somebody says, I have a hole here. The variables here are A, B, and C. You go someplace else and say, oh, I would like to fill that hole with a term here. The variables here are A, B, C, D, E, F, G. So now I have to worry because only A, B, and C are allowed, right? E, F, G should go away somehow. So, okay, we should check that only the variables that we like are there. Okay? And then if only the variables that we like appear, then we can use it. Are we secretly using any meta theorems? Yes?
Strengthening.
Strengthening. We're using strengthening because we're saying, even though we derive a term with more variables available, we are now going to use it with fewer variables available because some of the variables didn't appear, so it's okay. But that's strength. Maybe it's always good to keep in mind when is strengthening going to fail. So two typical examples of theories where they don't have strengthening are extensional type theory. Why is that? What is the defining feature of extensional type theory?
You can do equality reflection that doesn't appear in the free variables.
Yeah. There's a rule like this. If P inhabits the identity type AB, then A is equal to B. Okay? And if you now observe what's going on, any variables, there might have been some variables that were used by P. but P disappeared in the conclusion. So any variables that were used only by P are not used anymore. In particular, if P was a variable, it's now not used unless it somehow already appears elsewhere, but there may now be fewer variables used here. And so any rule that is like that, which you can manage to somehow do things so that you have fewer variables used downstairs, but you didn't abstract over the ones that disappeared. So let's compare this to lambda. Why is lambda? Because lambda is what I'm saying might make you think, oh, lambda is like that. Right? So let's compare. So here, you might think, oh, x is going to disappear. Yeah, but it's also going to disappear from the context, so it's okay. The problem is the context, the variable survives in the context, but it disappears from this part of the judgment. I think it's good to call it thesis. Okay, I have it on authority from the authority on Martin Löf type theory. He said once, Peter Lambden and I once asked for Martin Löf, what is this bit here called? And he thinks, he says, I think it's the thesis, and I like that. So if variables disappear from the thesis, but not from the context, then it's very likely you have to be really worried that strengthening is going to fail. Not necessarily, but in the chances are that that's going to happen. So so this is an example like that, because here you may have used some assumptions to produce P, and now you say, oh, okay, A and P are equal, but if you just look at this, the assumptions that were used in P, now they look like they're not necessary because they're not mentioned anymore. If they're not mentioned in A and B, then that's a problem. Another one is you have kinds of like strict prop, very strict prop in COP and AGDA. So there you prove the fact that something is true, and then you literally throw away the proof. And when you throw away the proof, you are now not using variables that used to be in the proof. So that's also another one. And these are always tricky, so you have to be careful. Anyhow, this is sort of a side remark. We are secretly going to use strengthening. And so if you're going to have an implementation of extensional type theory, you better recover strengthening, or you're not going to have any holes. And that's not going to be good. Okay? So let's just think about what we want to do. Okay, so let's consider an example. So I'm going to write holes with a question mark, and I'm going to name them. So in principle, you don't have to name a hole, but I'll name them because then we can talk about the hole H, and also error reporting can tell you which hole is problematic. But you could also write them just as underscore. But we're going to write this question mark something. Okay, so consider this. It's a function, takes a type, takes an element A of the type A, and then it does this. This is the body of the function. Okay, so what is this? Well, this is something that looks like the identity map with an unknown type applied to little a. So can you tell me what H is supposed to be? H is supposed to be A. How do you know? How did that happen? Well, we have a saying in Slovene. Well, maybe it's just my department. It's only in Slovene. It sounds better in Slovene, but you can solve a problem by sharply looking at it. So this is like you sharply look at this one, and then you know what it is. It has to be A, capital A, otherwise it's not going to work, right? So we're forced. Okay, how about this one? This is just an exercise to get going to understand what the problems are. So now I'm saying, okay, I have an X of unknown type. And then I have an A, and then I have a function that goes from A to type. And I I apply f to x. Can you tell me what the hole is? It looks like it's A. Is it A? Why is it not A? Because here there is no A. A exists from this point on because it was only declared here. So its scope of this A is there. So we are not allowed to say that G equals A. We're forced, so it's even worse than that. We're forced to say that G equals A because the only thing that could possibly work is that G equals A, which would be because of this one here. F really, really wants something of type A, and X is of type question mark G. So if anything works, it's going to be A, but A doesn't work because it's out of scope, because it's a variable that we're not supposed to use. Okay, is that clear? So in this example, we have to say there is no solution. Any questions? Okay, so what will be our status?
So that the ACTA error for
Yes,
for the two question
I was
marks.
fully relying on us that you telling us.
Yeah, so there's if you put the two question marks, you get it generates 7 meta variables, and then it gives you the error message unresolved metas.
So it generates 7 meta variables, 7 additional holes, and then it paints everything yellow.
Yeah, it becomes red, and the variables, there's one called _7, and it says error unresolved metas.
Okay. So
Which then.
But it did not say you are not allowed to have a hole here. It just generated lots of holes.
Right, and also if you add more
and
stuff.
it got unhappy with it.
Yes, and if you add more stuff to the file and you check, then it also colors the rest of the file, and it also type checks the rest of the file. It's only angry about that part.
It's only angry about that part. So it's at least localized anger.
Yes.
Okay, so what will be our strategy? So let's go back. So this is now a little bit annoying. We need to keep track. Okay, so here we have to know that H is allowed to mention the big and the small a. Here we must know that G is not allowed to mention anything. Right? Well, there might be some other global context that everybody knows about, but that's a different story. Okay? So, okay, option one is that when you have a meta variable, you actually remember in what context it appeared. You could do that. And so if you remember in what context appeared, then when somebody's trying to stick in a term, you say, oh, but is this term good in this context? That's a possibility. This means you're going to have meta variables in some meta context in which little contexts appear. It's an option, and there are tools that work that way. Okay? Another possibility is to say, I don't want to deal with this. I don't want to worry about whether a meta variable, whether I can fill a meta variable with some term according to some rules of variables. I'm just going to take the simplest possible solution. I'm just going to say, I prohibit any variables. A meta variable must always be closed. So this sounds a little bit prohibitive, because surely this one is not going to be closed. It cannot be closed, right? It will mention capital A. But we can still do it, and there are tools to do it this way. So we will require that meta variables are closed types, and then, because they're closed types, they can only be filled with closed terms. Okay? So let's go back to our example and see how we're going to solve this. So we have this example, and here we have to create a hole, but this hole now has to be created in such a way that I will be able to claim that the hole itself is a closed term, but nevertheless, it should allow the little a and the big A to be used. What do we do? You just have to be smart about what the type of the hole is. So here's what you can do. The hole H, you look at where it appears. It appears in the context that says I excuse myself for switching the fonts. It was too much LaTeX to have the fonts split. Okay, so it appears in the context where A is a type and the little a has type A, and its type is supposed to be type, right? You expect here to be a type. So now you take this and you universally close it. You just say, oh, okay, let me just take the product over all this stuff here of that, and that will be the type of my H. So we're actually going to introduce a meta variable H of this type, which I got by closing the type of the whole by everything that's in the context, and I alpha renamed things just so that there's less confusion. But now what do I need to place? What do I need to insert here? Because I cannot insert H directly. What do I insert in this place?
An application of what holds.
Right. So now I take H and I apply it to everything in the context. So I do this HAA. So this is a standard thing that you can do with meta variables so that they're always closed. And then because they're always closed, you don't worry about whether they're going to float over to some other place where strange variables have appeared or disappeared for that matter. Yeah. Now, what there will be unification? Let's look ahead. So what will happen? At some point, the type checking will figure out that this HAA business is supposed to be actually a capital A. So it will say, hey, I think H applied to A, little a should be that. Because that's what's going to happen, because it's going to say, this is a function, its argument has type HAA, so we need to check that this thing here, which has type A, has that type, we'll get that equation. So now that it has this equation, do you know how to solve this equation? Do you know what to put in for H? Yes. You can put in for H, lambda A type, lambda AA, because you just abstract, right? This is why you solve the equations in primary school, so that you know how to do this. Because you could just go, oh, H is this function. You abstract over these variables. In this particular case, it works. Okay. We're going to come back to unification, but let's now think about organizing this. So the meta variables, they will get, so let's now think about our type check. Okay. The meta variables will be created just like variables are created when you go inside the lambda. A variable is temporarily created. Meta variables will be created, but they're less temporary than bound variables. For a bound variable, you know exactly where it's going to be valid. You create a lambda, your bound variable will only exist in the body of the lambda and nowhere else. So you have precise control over where it exists. A meta variable is not like that. A meta variable is just going to float around, and then at some point, somebody somewhere is going to say, oh, I would like to set it. So that's a different discipline for scoping. You create it, and then it exists for the foreseeable future. And also, at some point, probably somebody should complain if it hasn't been filled in. But that's a different point. So what kind of a monad is it going to be? Yes?
States.
So yes, so the meta variables look like state, where you can create them on the fly, and then you can set them, right? When you know what the value is, you can set variable. If you discover that H is supposed to be this, then you should be able to define it. From that point on, it should be defined to be equal to that. Can I set a meta variable twice? Like if I already discovered what it was, and then I discovered that it's something else, and I just set it again. Is that a good idea? Yeah.
I would say generally, well, if those two things are also two meta variables, then maybe it's okay.
Or if those two things happen to be equal, it's okay.
Yeah, but
Yes.
otherwise it's a problem, and we
I mean,
want to
in
fail.
principle, it could be quite bad. Because half of your proof you're going to think that H is that, and the other half of your proof you're going to think that H is something else, like integers. That's probably not a good idea. Yes.
But I could also have a different semantics of meta variables, where just like when you solve a Sudoku, you can sort of make a guess. You say, I'm going to guess it's 3, right? And I'm going to solve a little bit on Sudoku. Oh, it couldn't be 3. I go back and set it to something else.
Okay.
You can sort of solve meta variables in
So
that way.
I think your idea is important because yes, we might be in a situation where we take a wrong step, especially if we're trying to fill in holes using proof search. Right. It's not just unification. Maybe you have an automated theorem prover and you tell it, you fill in this hole. And then the automated theorem prover says, I have 17 proofs of this fact. Which one would you like? And maybe then you want to try 17 different options. In that case, your monad is going to be even more complicated.
Well, it's
Because
going to
you
be
have
the
to
list.
support backtracking, right?
It's the list monad, right?
But with state.
Yes.
Yeah, so, right, the monads are kind of blowing up in our faces here, right? So it might be monads with state and non-determinism. Yes.
So actually, like another form of like extension is like type classes. And in Rock, there are two implementation. Type classes can equal structures. And one is a proof search. And the other one is modification of the conversion algorithm, or the unification algorithm, sorry. And so that's really two different views to see it. And the control you get in each case is not necessarily the same one. And type classes don't scale very well. Though in Lean, they implemented them better and apparently it works. So it's not so clear where you want it.
He ups you by one order of magnitude in the complexity of the monad.
So I would really like to discuss that after the lecture. I didn't get the whole thing actually.
So it might even be more than one monad. Who knows? Depending on your strategy.
I'm still kind of thinking about G that wasn't solvable.
The G bothers you.
Yeah, I was wondering if maybe there is a world where it's okay to solve G for A, because maybe that's what the user wanted, or is this really something that we really never want to do?
Well, okay, so I think it doesn't make sense to say that G is equal to A because that's not it's not well scoped. You don't even know what A is at that point.
Yeah, okay.
So you have to answer that. I mean, sure, you can do it. I believe there are programming languages where when it encounters a new variable that it has never seen before, it says, sure, it's probably equal to 0. You could do that, but I wouldn't recommend it in a proof checker.
Yeah.
Okay, so we need to change a couple of things. So let's look. So one question to discuss is, are meta variables really different from variables? I was saying earlier, obviously so. But now we're saying a meta variable is something that has a type. That sounds like a variable to me. Okay, so it's the discipline that makes them different. It's what's happening with them that really makes them different. It's not what they look like. They all look like variables, but what you do with them is different. And that's why you want to distinguish them, because when you hit a meta variable in unification, you do one thing. When you hit a variable in unification, you do another thing. So that's why we're separating them. This is, so to speak, intentional information. You could be in a position where meta variables are actually different from variables because they can carry the kind of information that variables cannot. Like, for instance, you could have meta variables witnessing judgmental equalities. And then that's not something you can do with a bar. Right? Okay, so there's this addition now to our types. And then we need to change. So if there are two new lines here. So it used to be identifiers that just map concrete strings to abstract variables, and then there was the variables that map abstract variables to their typing information and possibly definitions. So now we're going to add metas, which look just like variables, surprise, surprise. But this bit, this part of the context will behave like state, whereas this part of the context will behave like a reader monad. And so they're separated. There is a mysterious locals here. And so these locals will appear. Let me explain why it's there. So maybe like this. So if I know all the variables stored in a balanced tree, then I forgot in what order they got introduced. The variables were introduced in some order. When I was going inside the lambda, inside the lambda, inside the lambda, I get variables. And I'm throwing them into this map. This is a self-balancing tree. There is no order. So if I'm ever in a position where I need the order, then I will be very sorry. Do I ever need the order in which the variables were balanced, were introduced? So far, not. But now, yes. Imagine that my context here is unordered. It's just some map. I don't have any ordering on it. If I don't have any ordering on it, when I create H, how do I know in what order they have to make these pies? I don't. So I could try to go, like I would go insane, study the dependencies and do a topological sort and get some order that works. Why? Why would we do that? So isn't it better to just store the order? Also, when you store the order, we are going to have a double use for it because we will know which variables are the local ones and which ones were introduced at the top level. Because this is going to list just the local variables in the order they were introduced. So in other words, these are now De Bruijn indices, and I'm back to De Bruijn indices. Because they tell me how far long ago a variable was introduced. Well, that's the index. It's used so far, it's going to be used to correctly compute these pi types. Okay, we already said that variables behave like the reader monad and meta variables behave like the state monad. So our new monad, so yesterday, it didn't have this. It took a context. You have a context, you run your computation in the context, it will read from the context and compute something. But now it may modify the context. And so you need to return the new context and whatever you computed. So this is like the state, except that only part of it is the state. It's just the metas that are the state, and the rest is not stateful. So then this looks now like the state monad. This is the standard definition. So because now what's going on is I pass the state to the first computation, I get out the value and the new state, and then I pass the new state to the second computation and the value. There is a little bit of trickery going on where we introduce a new local variable, right? So there we have to be careful. I wonder if I could just, I will dare showing you the so let's look at this one. Okay, so what is this one? This one is used when you have a new, when you introduce a new identifier. Maybe it's easier if I first show you how it's used. And let's look at the lambda. Here. Okay, let's read the code for lambda. And this is presumably inference. Yes, this is inference mode. So first check that U is a type. Okay, and now I need to check that E has the correct. I need to infer the type of E, but I need to do so in a context extended with X. So how do I do that? I use this context with ident thing where I tell the context extend yourself with an additional identifier X of type U. tell me what abstract variable you used, you created, and then I'm going to do something. And then you do something. In particular, you do infer E, and then you calculate the result. So how does this with context work, with ident work? Here's with ident. Well, okay. Calls extend. Thank you. We have to look at extend, but we don't have to look at extend. What we have to look at is the type, the monad discipline. Okay. So the monad discipline is going to go like this. This extend will create a new context called local context. Then we're going to run our computation. We'll tell the computation, hey, this variable got created, and here's your extended context to run in. And this thing is going to tell us what it did with the context. So it could change some meta variables. So what I pick up is the result, and I only take the metas from the output context. And then in the original context here, I use the original context, but with the new metas. So I'm really rolling metas as states, but not the rest. So it's some monad. I mean, Haskell people, they wouldn't even blink, see this kind of thing. So it's totally okay. So that's the thing that you need to do. Okay, so let's now discuss how you fill in the holes. As I said, there can be very many ways of filling in the holes. You ask the user, you ask an automated proof search, you ask the type. By the way, type class resolution, that's just, as far as I can tell, that's a different name for Prolog, isn't it? Yeah, it's Prolog. I think we should just call it Prolog, it would be more honest. So you write little Prolog. When you write your type classes, you're really writing little Prolog programs.
The only thing is that it's Rock, it's old ACI code, and it's far from being as rigorous as Prolog.
Okay, well, that's at least one PhD there, right? Okay. So we are just going to look at one case of how holes are filled, and that's unification, because that is a very basic algorithm that's good to know anyway, because it's always good to have a mental model of what your proof assistant is doing. Okay, so what is unification? Unification is equality checking, but it's more flexible because on the fly, as it's doing equality checking, it will also solve equations as necessary. So if there are any meta variables, and if it will see an opportunity to say, oh, because this is equal to that, it's because this is supposed to be equal to that, therefore some meta variable I can calculate it. So it'll do that. So it's equality checking combined with solving equations. It's the basis for many, many things, including Prolog. And Hindley-Milner, polymorphism, and so on and so on. Okay, so where does the opportunity to solve equations arise? So first of all, does it arise in the extensionality phase? Let's remember, what does the extensionality phase of the algorithm do? The extensionality phase will work like this. It says, somebody asked me to show that it was this symbol. Somebody asked me to show that U equals T at type A. And then what you do is you normalize A. And you look at what comes out, right? And if a product comes out, then you know what to do. You do something special. Right? And if you had other types, if anybody solved the exercise from the first day and thought about what to do about the unit type, they may have discovered the unit type with the extensionality law. So then, if it's the unit, then, for instance, we just say, yep, they're all equal. We don't have to, we can stop checking. Yeah. And there are other laws like that you could use. So is there an opportunity here to solve an equation? I don't really see it, unless somehow during normalization it would happen, but not really. it really comes up during the normalization, during the second phase, where you are comparing normal forms. So one of the things that can happen is that you are asked to prove this equation. Oh, there should be, okay, so if it's going to be the normalization phase, this is going to be it's going to be the other symbol, really. So here's my error count, right? It should use this symbol from the slides. It's an untyped equality and so on. But anyhow, we're supposed to prove check that this equals to this. And we see a meta variable applied to stuff equals some right-hand side. And now certain conditions have to be met. So first of all, M must be an unsolved meta variable. It should not have been set beforehand. Actually, if we see this as a normal form, then we are guaranteed that it has not been set. Because if M had a value, then normalization would use that value and make progress here. So we know that it's not going to happen, that we are trying to compare these two normal forms, and M has a value, because then it wouldn't be a normal form. So this one, if you got here, this one is satisfied. Then this is here, they need not be variables, but I want them to be variables, because when they are variables, then I can do lambda, 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 lambda. So do I just give up if they're not variables? No, of course not. I normalize them, right, to see if they are all variables, and they must be distinct variables, it turns out. Okay, so if two of those are equal, things get more complicated. There's sometimes a way out. I'll give you a reference to where you can learn on improvements, but I'm doing I'm doing just the first very basic case. And then what also has to happen, because we know that we want this to be a closed term, it shouldn't have any free variables other than the ones that are mentioned here. Yes?
Is it because sort of if you allow to repeat a variable, then the language becomes context free? Language of sort of
start getting multiple solutions.
Yes, like a sequence of variables where you require a variable to repeat in the future is no longer regular. Equality is decidable for regular expressions, but not for context-free grammars. Is that the problem?
Possibly, but the answer that I want to give is you start getting multiple solutions.
Okay.
Yeah. Because you see x, and so whenever you see, suppose x appears here twice, and then here you see an x. It could be the first one or it could be the second one. You don't know which one. You have two possibilities, and so then you get lots of possibilities. Okay, now under these conditions, do we know what M is supposed to be? Yeah, we just lambda abstract it. And then it's going to be the right thing, because if you now plug it in and you reduce, you're just going to get the right thing, because those were variables. Yeah. That's the idea. That's what we implement. This is the very basic unification. It doesn't work very well. It will quickly hit examples where you wanted to do more. In general, there isn't there is an optimal unification algorithm, but you would never ever want to implement it because it's it's complete level. I mean, it's like it's super complicated. It's super inefficient. So usually what people do is they implement subclasses of possible things that they could solve for. You see, because I could solve, by the way, I could solve every hole. Okay, here is an algorithm that will always succeed on every hole. Try all possibilities, just keep enumerating them. And when you find one, that's okay. But that's not something that's realistic. So you have to. We want to do something that is somewhat efficient. Okay. Anyhow, this is a basic version. Yes.
So the algorithm you're talking about is pre-unification. Yeah, pre-unification. The one you're mentioning that is not used because it's too complex.
I'm suggesting exhaustive enumeration of all derivations, which strike you as entirely.
So this is pattern unification, right?
This is pattern. Oh yeah, sorry. Yes, thank you. This is often called pattern unification. This is
Right.
a limited kind of trying to solve equations, and it's even within pattern unification, just the very basic.
Yeah, and the one you're touching about is via pre-unification, right?
Sorry, what do you mean by pre-unification?
The one for the one where you don't have any restrictions, like higher order unification. It's called pre-unification
Oh, I
because
see. Yeah.
it's solved for flex pairs.
So maybe for the general audience, there are conferences, books, and PhDs about unification. And there are very many different kinds, and they can easily be very demanding in terms of complexity. And it's just sometimes they're undecidable and so on. So you should not ask for too much. And I am not asking for too much.
Yeah, so I was curious because there is like, well, I come more from the theorem proving ATP. So higher order unification is quite usual thing people implement. It's undecidable, but it doesn't stop people from using it.
Thank God.
But the thing is that I'm curious in this functional programming world, how common is it to implement that algorithm or to use it?
Okay, so if your goal, so it depends on what you want. When in a proof assistant, people write down underscores, and when they have implicit arguments, what they usually expect is that there will be exactly one solution. So if you discover that there's more than one solution, that should be an error. You shouldn't just give them the first solution. Right? So this scenario is different from automated theorem proving, where you are happy to find any solution. Of course, you want a good one, but you live in a world where there are always many solutions. You just want to get one of them. And higher order unification is almost never going to have unique solutions. And so kind of doesn't come into play because people don't want multiple solutions. Why don't they want multiple solutions? Because if the machine sticks behind their back the unification algorithm without telling them what exactly happened, puts in something as the solution, and you don't really see it, and then 2 pages down, you have an error. And now you're wondering, why is this error here? And it can be quite difficult to realize that the error came from the fact that you unified the wrong way 2 pages ago. And in fact, there is a scenario in proof assistance where this precise thing happens when people are not careful. And this happens whenever the machine fills in a hole with something that is not intended. One such example being type classes. It's a lot of fun to debug type classes when you start getting the wrong type classes inferred by your little prolog. So my answer is yes, this is very valuable if you're trying to do automated search, and I would imagine that proof assistants that have tactics for automated search would want to use higher order unification. But when you don't care which solution you got. Any other questions? Yes.
One important part of unification is also this occurs check.
Yes.
And I was wondering whether we run into this here or.
I think we already solved it here.
Okay.
Because I guarantee, as I said, this is the dumbest possible unification you can think of. This one will guarantee that this E gets a closed term. So M cannot appear in here because the only things that can appear in there are those variables and nothing else.
Right.
Okay. What are some dirty details? There are lots of dirty details here. Okay, so somebody has to complain at some point that not all meta variables are solved, because if you stick in a bunch of arguments, you create some holes, and then everything has type checked, but the holes are not filled in. Are you done? No, because maybe one of your holes it has type empty. You're definitely not done. You need to fill in the empty hole as well. So a proof is not done until all the meta variables are actually resolved. Question, do you need to resolve only the meta variables that are actually mentioned, or all the meta variables that were introduced? Because maybe a meta variable was introduced, but it's not used anywhere. Do we have to worry about it? What's an example of this? I have a stupid proof assistant that introduces too many meta variables for some reason. I have an example. Okay, I can also be a stupid user. That's easier. So I do let it's a hole in, and now I am not going to use count. Okay, so here I have something that doesn't use count. Do I have to complain if this doesn't get filled in?
Yes.
Why?
So we had a similar bug with the count condition in Rock. The issue is that if you start evaluating in goal by value, then you're gonna get issue because you're gonna try to evaluate something that in goal by name you wouldn't have evaluated. And so for a while when you're extracting to OCaml, Rock, you could get something that was just not terminating. Because the let like this was disappearing.
So you're saying it mattered because of guard conditions.
It matters because if you start reducing stuff when you check stuff, then you make variables disappear, but with another strategy, it won't disappear.
Okay.
Then you fill it with an underscore.
Yeah, I mean, this is an underscore, right? When I write this, that in practice, this would be underscore. I probably have to be in type checking mode, come up with a type. Could we use strengthening here? And say, well, if it doesn't appear, it doesn't matter. By strengthening, so we would want strengthening for meta variables, probably. I don't know. Okay, think about it. Yeah.
So if the user at some point uses cow in their program, I mean,
Yes.
you have a program, you're not done with it, so you have sort of cow hanging around there. Suddenly you use it, now you get an error 2 pages later. So it's sort of like I think that's sort of.
Okay, but that's a global cow. My cow is local. It's only scoped here, and I look and it's not there. Does it matter? Yeah.
Your solution that was like we use strengthening to ignore cow basically amounts to like elaborating and providing the user in the kernel a different proof term. So then you have a discrepancy between what you would have at top level and what would you have in the kernel.
Sorry, but why do I care about a camel? I'm asking whether
No,
this is
in
valid in
camel,
type theory.
It's not a camel, it's a cow.
Not in the camel, it's the kernel.
Oh, in the kernel. Oh, sorry. If I use different. Okay. So your point is this: some meta variables may disappear when I use one normalization strategy, but may hang around when I use a different normalization strategy. So in one case, I think I don't need it, and in another case, I think I need it. Well, do I need it? Do I really need it? Yes.
So it doesn't matter if you need it. The programmer wrote a meaningless program, right? And I should have not specified cow. I should erase it. It's an error.
It's an error to write useless code.
Yes.
Ah, okay. Well, that's a good attitude. So why do you write?
Well, you can, like Actor, you can make local.
I have a question.
Okay, yeah.
Why do you write programs in Haskell? You only ever write code that will get evaluated. Why do you write code in Haskell?
Well, I run it all the time.
So,
As opposed to Actor programs that I actually don't run, I only type check them.
so what I would really like to get across is that it sounds maybe like some of these questions sound easy, but they're not easy, and they are sources of bugs in real proof assistance. So, for instance, because somehow you hide something somewhere by doing these things. So if you want to be perfectly safe, you will paint things yellow unless all meta variables are filled in. That's the safe way to go. If you're going to do anything else, you better have a proof that you're okay. It might be the case that the presence of this meta variable that is not filled in convinces you, as you were pointing out, maybe it will convince you that something terminates or something like, or you delete it. You say, oh, it terminates, oh, somehow I don't need it. It can be some form of proof irrelevance. And as soon as you have some form of proof irrelevance somewhere, then you have to be really, really careful because you don't have strengthening anymore. Okay, so let's go on. Okay, there's one thing we did not discuss. I here said, oops, here I said, oh, suppose these are variables, then we can do it. Okay, but what if these are local variables and some of them are defined to be equal to something? What then? Suppose I know that x1 is defined to be 7. Then this starts to look very suspicious, right? So that's a strange question. Okay, what if E contains a variable y, which is not one of these, but y has a definition? Then we could get rid of the y, because if E contains y, y has a definition. I stick in the definition, y is gone. So that's a complication that you would need to think about. If I have defined variables, which normally I do, then that complicates, that interacts with unification. I'm not going to solve all the problems. I'm going to now list dirty details here for you to know what to beware of should you choose to implement something like that. Okay? Now, it's not really true that the meta variable has to be entirely closed. It may refer to some previously defined constants at the top level. So you really start to, you start thinking, oh, I want a distinction between local and global things. Things which are guaranteed to be around forever. Things that are guaranteed to be around forever, everybody can use, so it's okay if my meta variable uses it. So the algorithm I suggested, you could also try running it, is going to answer our question. So here's our running example. A is a type, little a is a big A, lambda x, unknown h. Earlier, you told me that this h is supposed to be capital A. You run this in the implementation that I described, that you have on the in the course materials. You get this answer. Is it the correct answer? Your mind hates doing beta indices, doesn't it? So let's think. Here's x. This x is supposed to have type A. Okay, here is its type. It goes from here to here. What is this? This is a lambda that goes from here to here. So it's a lambda where A1 will be A, and then it's applied. Then the little A1 will be the little a, and then we return the A. So this actually reduces to capital A. So it's okay. Is this something you want the user to see? Probably not. Yes, you do? Oh, okay. So you probably don't want the user to see this. So now what do you do? Question, should we just normalize all the way? Why not? It might go boom, right? This is like unrolling all the definitions. If you go to, you should try this. You go to a differential geometry class and you ask the professor to unroll one definition, any definition, all the way back, and that's it. You will be sent out. So you don't want to do that. So you have to unroll, you have to reduce just the right amount here. There will be an additional complication with local definitions. You can play with the implementation to see what happens. Look into the tests. There are unit tests, and they have some examples where you have interaction with local definitions, and those create even uglier solutions because the local definitions get inserted as needed. So I don't think I want to say much more today. Let's see. We said, yeah, you can solve more equations. We said, yeah, you can normalize away the beta indices, but not much. Oh, here's another one that we did not address, which you would want to do very early on. Okay. So let's consider this example. So now again, I have a type and I have an element type. And now I say, here's an f of an unknown type. Here's my whole. Please infer this type, and it's f of a. Can you tell me what h is?
A to A.
A arrow A. How do you get the fact that this is A arrow A?
Looking at it sharp.
Look at it sharply. Okay, you learn well. You learn fast. So when you look at f of A, here, you will say, oh, the product, let's see, bidirectional type checking. What will it do? It will do the following thing. We have to infer the type of A. The first step is you look at F and you infer its type to be a product. And in this case, well, some product, let's call it B, C. And then after that, you check that this little a here has the type B, and then the answer is C with A for X. That's the rule. What will happen if the type of H is a whole? If the type of H is a whole, here we're going to start normalizing a whole. And we will wish that it normalized to a pi. But it doesn't. It's an unsolved meta. But we can do something. What is it that we can do? Yes?
Create a pi and then two new meta variables.
Yes. So I create, I set H to a pi. When I see this, I set it to a pi, which has two new variables. Let's call them H, G, K, and that. Yes. You need to think carefully about the types of these things, and it's not so easy because H is probably some sort of a product. It gets a little bit messy, but the idea is here. You say, oh, I can introduce two new meta variables on the fly, say that H equals this, and proceed. And now when I proceed, this one is going to be G. And this one is going to be K. So now here, I will check that this one is K, but this is a variable, so it's going to emit A, and I will have to check that A equals K, so, sorry, G. So this way I will solve for G. Yes. When will I solve for K? That's the other step, right? Because it will force the outputs to be the same as in. And that's certainly the kind of thing you want to do. Now, I only presented the very basic stuff. We talked a little bit about the fact that there are some monads. The monads looked a little bit unpleasant, but they're there. There is quite a bit of finicky stuff. If you really want to know more, I highly recommend to learn from Andrej work. Start with the elaboration zoo. It's a progressive sequence of easy examples. He starts with untyped holes, by the way. Somebody asked about untyped holes. The first version he has are untyped holes. Even better, it's all written in Haskell. And so he will show you also how to do the Brownian indices and this and that. So I highly recommend reading this and trying it out. It has much more than what I covered here. Okay, I only covered the basic stuff. And I think that's it. Thank you. Yes,
If there's no question, maybe I can make a comment.
sure, please do.
So, like in Rock, there's 3 implementation of unification,
3,
at least.
at least, okay.
And so the issue is that some implementation we know are better, But once you have a CI with 5 million lines of code, unification is so delicate that you can't change something without breaking something. And so because of that, you can write a new development, a new unification, and improving unification without breaking everything is very complicated. And then you throw in unification a bunch more kinds of meta variables. You have universe meta variables. Now you have sort meta variables, and it gets a big mess. And that's why it's time to improve unification. So in, for instance, type classes overall with a new implementation, but now that they have been using it, they kind of stuck changing it.
Yeah, and I think it's the bottleneck, right? So yeah, so it's dark art. I should quote Gavin Bierman here. Gavin Bierman is one of the lead developers of Java, and he likes to say, "Today's solutions are tomorrow's problems." Okay, thank you.